Moving into chapter 11 now, we're going to look at techniques of differentiation with applications. Now, here's the cool part. So, now we can use shortcuts. If I ask you to compute the derivative using the definition is f prime of x is equal to the limit as h approaches 0, oh that's ugly, of f of x plus h minus f of x all over h. So if you're ever asked using the definition, this is the definition, this is what you have to use. But these rules, this is where calculus gets easier than algebra because it's not actually focused on algebra as much. We're going to use the results of 100 years of hard work by others. And what they found, they being mathematicians of the past, is that in this limit definition of the derivative, if n is any constant, all right, any number, and f of x is equal to x to the n, then the derivative is n multiplied by x to the n minus 1. So we multiply by the old exponent, leave our x variable, subtract 1 from the exponent. And we could show this through the limit definition for several versions of n, and then you might use mathematical induction to prove it if that's along your line of things, but I'm not going to. So power rule is our first big rule. This is a really important rule. We're going to use this all the time. I would totally put this on a note card so you can look at it while you're doing your homework. Let's talk a little bit about differential notation. Differentiation, d dx, means the derivative with respect to x. Thus, d dx of f of x, it's the same thing as f prime of x. The derivative of f of x with respect to x. So x is your variable, take the derivative. Is it a prime notation or differential notation? If y is a function of x, then the derivative of y with respect to x is dx of y, or more compactly dy dx. So dy dx, actually d dx, is an operator. It tells us to do some type of mathematical action. Just like addition tells us to do something specific. Division tells us to do something specific. A square root tells us to do something specific. All of these are operators telling us what to do. We just have a new symbol. Our new symbol looks like a fraction, talks like a fraction, sometimes it walks like a fraction, but it's not a fraction yet. It will be. It's an operator that says take the derivative, use x as the variable. All right. Second rule, very important rule. Derivatives of sums, differences, and constant multiples. If f of x and g of x are any two differentiable functions, and if c is any constant, then the functions f of x plus or minus g of x and c multiplied by f of x are differentiable, and the derivative, let me see this right, the derivative of a sum or difference, right? F of x plus g of x, take the derivative, is equal to, so the derivative of a sum or difference is equal to the sum of the derivatives. Mathematicians are actually sticklers for words, and this switching of the order, huge. Also, if you have a constant multiplied by a function, you want to take a derivative, you can find the derivative and then just multiply that by the constant, all right? So the constant multiple rule. And I put them both in words here, fully typed out words instead of my chicken scratch. The derivative of sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives. All right? Sum, keep sum, subtraction, keep subtraction. The derivative of c times a function is c times the derivative of the function. And looking at our two different notations, our d dx versus our prime notation, the prime notation is nice and compact, one line. A differential notation says the same thing. It's just a little bit more complex because there's more symbols. All right? And you can see why some people prefer the prime as opposed to the d dx, especially when you're taking notes on line note paper. So now that we could take the derivatives of all powers, we could add and subtract pieces, and we have constant multiples. Now I can find the derivative of all polynomials, and we never have to do the f of x plus h thing. Now, let's take a look at this. Suppose I have a function y equals cx, right? Instead of m, I'm going to use it c. This is just a graph like this. Remember, a derivative is a slope. What's the slope of this graph? A derivative is a slope. The slope of cx, I mean, look, we've even written it right here like a linear function. So if derivative is a slope and the slope of the linear function y equals cx is c, it makes sense that the derivative of cx is c. And if we have a constant function, right, like y equals 2, whatever it happens to be, y equals c, any constant, a nice horizontal function, what's the slope of that horizontal line? That slope is 0. So are these difficult to know and understand? No. But they're the ones that frequently get people in trouble the most. So make sure you remember these. These are the third and fourth rules that I would put on my note card if I had a note card of derivative rules. In general, the derivative of the absolute value of x, so the derivative with respect to x of absolute value of x is absolute value of x over itself. Notice that the derivative does not exist when x equals 0, and that's because the graph of the absolute value has a pointy spot, and that pointy spot's a bad thing when it comes to derivatives. So let's just find some derivatives. I'm going to find a color that I don't use anywhere else. Let's go magenta. That seems regal. Find the derivatives. Now remember, if I have x to a power, my derivative, according to the rule, says you bring down that power, you leave the variable, and then you subtract 1 from the exponent. So I'm going to write exactly that. If f of x is x to the fourth, right, my n is 4, f prime of x will be 4 times x to the 4 minus 1. So we do this subtraction. I'm going to try to do this subtraction, at least for today's notes. By 11.2, I might not always write this subtraction. Sometimes I bring it back, but it eventually gets phased out because you can all subtract 1. You know how to subtract 1 from any number. I could give you any number, and in your head, you could subtract 1. So eventually I stop writing it, but not yet. All right, so the derivative of x to the fourth is 4x to the third. Done. That's all the work that needs to be shown. And if you're on WebAssign, this answer is satisfactory. Remember, n can be any number, so if f of x is x to the negative 1, our derivative will bring down that negative 1. We'll leave the variable x where it was. We'll subtract 1 from the exponent, so negative 1 minus 1 gives us a negative 2. And you know how mathematicians are lazy. We frequently don't write 1s, all right, but we'll keep that negative. So instead of negative 1x to the negative 2, you might write this in many different ways. Both of these completely acceptable as answers. Notice that negative's out there. But my problem started with negative exponents, so I don't really care that much if I use negative or positive exponents. Stella says hi. Sometimes if you growl at her, she does better. I apologize for doing that on the mic. So now we have the sum and difference rule, we have the power rule, we have the constant multiple rule. Check this out. We could take the derivative of a polynomial. So we're going to focus one thing at a time. F of x equals negative x to the third. So I'm going to leave that negative alone because that's my constant multiple out front. I focus just on the x to the third, and I bring down the 3. I leave the x, I subtract 1 from the exponent. Done. Now I take the minus sign, and the 3, that constant multiple out in front, I just leave the minus 3, and I take the derivative of just the x squared. The 2 comes down in front, I leave the x alone. Original exponent of 2, I subtract 1, so I get 2 minus 1. Fantastic, took the derivative, and now we'll finish off with the minus 1. But what's the derivative of any constant number? Any number that does not have a variable associated with it, the derivative of the constant called 1 is 0. All right, so the derivative of constant is 1, remembering this rule. We use the rule, write it down in detail, and then we clean it up. So the negative 3x squared minus 3 times 2 is 6. 2 minus 1 leaves us a 1, so an exponent of 1 we very rarely write, but you could if you wanted to. We almost never write a plus or minus 0 unless we're showing an operation like this one. Let's look at example number 4. I believe it's all examples from here on out, but yeah, we're only halfway through the pages, so this is probably going to be another 20-minute one. I apologize. F of x is 2 over x minus 2 over x cubed plus 1 over x to the 4th. Many times we'll start with a rewrite. All right? Rewrite the function using negative exponents in order to look at it like a power function. All right? So instead of 2 over x, that x is from the denominator, that's 2x to the negative 1. Minus sign. 2 over x to the 3rd, that x to the 3rd is in the denominator. To move it to the numerator, it's now, the minus 2 is all cool. It's where it needs to be. The x is the only thing that moves, so the x is the only thing that has that negative exponent. Plus 1, cool. Denominator of x to the 4th, it crosses the fraction bar and becomes x to the negative 4. Now that we have everything written like a power rule and not a fraction, we can take the derivative. Leave the 2, that's the constant multiple rule. Derivative of x to the negative 1 is negative 1, x to the negative 1 minus 1. Leave the minus 2, that's the constant multiple rule. The derivative of x to the negative 3 is negative 3, x to the negative 3 minus 1. Took the derivative, done with it. Plus sign and 1. Derivative of x to the negative 4 is negative 4, x to the negative 4 minus 1. So I rewrite so it looks like the power functions, all right, even if that has negative exponents. We take the derivative using the constant multiple rule, the sum and difference rule, and the power rules. And then we simplify. Negative 1 times 2 is a negative 2. Negative 1 minus 1 gives me an exponent of minus 2. A negative 2 times a negative 3 multiplied to give me 6 as a coefficient. A negative 3 minus 1 gives me a negative 4 as an exponent. Don't forget your x's. The x's are the most frequently forgotten part. Don't forget your variables. A plus 1 times a negative 4, that's a negative 4 coefficient. X to the power of negative 4 minus 1 makes a negative 5. Now, in number 2, our problem started with negative exponents, so I could leave it with negative exponents. But in problem 4, our problem started with positive exponents. I used negative ones to make it easier on myself, but I'm going to answer with positive exponents. Always answer in the form the question was written. If it gives you negative exponents, answer in negative exponents, no big deal. If it gives you positive exponents as a final answer, or as your initial answer, make sure you use positive exponents in your final answer, even if you need to take them across the fraction bar. All right. Yes, you could factor out a 2 over x squared, but we're not factoring here. We're just finding some derivatives. T of x equals 3 square root of x, 3 absolute value of x minus the square root of x. Remember, the square root of x is x to the 1/2. You will see this so many times in chapter 11 that you're going to be sick of it by the time we get to chapter 12 and keep using it. So the first thing I'm going to do is rewrite this because I don't like square roots. I like powers. I could use numerical exponents and find derivatives a lot easier. So I rewrite it instead of a radical form into a rational exponent. Now I could take the derivative. Remember, we were given the derivative of the absolute value of x is the absolute value of x over x itself. So this is definition, all right? I think it was formula number 4 I suggested on your note card. Leave the 3 alone. Derivative of the absolute value is the absolute value over itself. Leave the minus sign. The derivative of x to the 1/2, I'm going to bring that 1/2 to the front. I'll leave my variable x, and I'll take in my exponent 1/2 minus 1, the original 1/2. Subtract 1, always subtract 1 when you're finding a derivative. So 3 square root of x over x, not much I could do there. Here, however, 1/2 minus 1 is a negative 1/2. But since this all started with radicals and no rational exponents at all, I'm going to take 2 steps. First step, I rewrite the 3 absolute value of x over x. I leave the minus sign, but now I take this x to the negative 1/2. Just the x has the negative 1/2 power, so just the x with the 1/2 moves to the denominator. Notice the 2 was already there. We already have a fraction built in. So what we're doing really is picking top or bottom, numerator or denominator, when it comes to setting our x to the negative 1/2. And we already have a fraction line, so just put it down there with the 2. We started with a radical of x, however, instead of x to the 1/2. So the only thing I do as my final step is, instead of calling that 1 over 2 x to the 1/2, I call it 1 over 2 square root of x. All right. Now, a new type here. We're going to find the equation of the tangent line. Remember, equation of the tangent line, anytime we're looking at a line, we're looking at y minus y1 equals m times x minus x1, close parentheses. All right, so always, equation of the tangent line, I automatically jump here to the graph of the given function at the given point. So what we know is our given point is x1, y1. What we know is our slope, m, is the derivative. And specifically, the derivative here at negative 2. There's a negative inside of that too. So we have our x1, we have our y1, x and y are general. I only need to find my m. Anytime it wants me to find the equation of a tangent line, I need 3 things. 1, 2, 3. A lot of times the point is given and takes care of 2 of them. Slope, derivative. Slope, derivative. I cannot say it enough. So we take the derivative, f prime of x. When f of x is x to the 4th, my derivative, we bring down the 4. Leave the variable x, subtract 1 from the exponent, 4 minus 1, so we get 4x cubed. Now our slope at this point, the slope is the derivative at negative 2, which is 4 times something to the 3rd power. Didn't mean to touch my screen there. 4 times something to the 3rd power, our something is negative 2, so we'll evaluate. Negative 2 multiplied by itself 3 times is negative 8. Negative 8 times 4 is negative 32. So now I have put in my y value, y minus 16, equals slope negative 32 times x minus 2. I've put in my 3 pieces of information that are specific to this function and this particular point. And all I do now is simplify. Here I combined x minus a negative 2 to make it x plus 2. This answer is totally acceptable. In fact, if you have online homework and it has a blank like this, watch for the y equals on the outside. Probably what I would put is negative 32 times x plus 2. And then I would add this 16 to the other side. Now, I do simplify it here. Distribute the negative 32, so negative 32x and negative 64. Add 16 to both sides. Negative 64 plus 16 is a negative 48. So this is this is beautiful. This is pristine. This is the equation we want. But this is quit while you're ahead. Quit while you're ahead. Where do you mess up mostly? Do you mess up the calculus? No. Calculus is easy. Trust me, calculus itself is easy. Where do you mess up? Personally, I mess up on the algebra. So if I could do the calculus and nail it, and as little algebra as possible, I know my calculus answer is going to be more acceptable. All right. So that's a lot to look at. Don't forget, these notes are available also on Blackboard if you want to take a look at them before I get them all dirtied up here. All right, back to normal. I don't know why I felt I needed to erase those. I apologize for wasting your time. f of x is 1 over x squared, x value of 1. So now I'm not given a point, but I still want the equation of a tangent line. I have the x value, so I can evaluate the function f of 1 when x is 1. F of 1 is 1 over 1 squared, which is 1. So I have my point. I now have my x and my y. These two are taken care of. So I've used the function once to get the y value, because anytime I want a y value, I always use the original function. If I want a slope, now I'm going to look at the derivative. So instead of looking at 1 over x squared, that's going to be x to the negative 2. Write it with negative exponents. Much easier to use the derivative rules. Bring down the negative 2. X to the negative 2 minus 1 equals negative 2 x to the negative 3. And because I have to evaluate it, I'm going to simplify back to positive exponents. I don't want to evaluate any number to a negative 3 power. I'm capable, but I don't want to. So I simplify to positive exponents first. Now I'll use my x value of 1, find the actual slope. My slope for this problem is the derivative evaluated at 1, which is negative 2 over 1 cubed. 1 cubed is 1. Negative 2 divided by 1 is negative 2. And I have my third piece of the puzzle, so that I can simplify. Now I have negative 2 times x is negative 2x, and negative 2 times negative 1 is a positive 2. And when I add this one to the other side, I'll end up with y equals a negative 2x plus 3. Hardest part? I don't know. The derivative is pretty easy. This step for me is always the easiest. It's the algebra, right? When I'm evaluating or when I'm manipulating fractions or functions, equations, that's the hardest part. All right. So find all values of x, if any, where the tangent line to the graph is horizontal. All right, so a tangent line. Anytime we're talking about a tangent line, we're talking about slopes, derivatives. Horizontal means the slope is derivative. Slope is equal to 0, right? So instead of find all values of x, if any, where the tangent line to the graph is horizontal, a mathematician's way of saying it, you could say find all values of x, if any, where the derivative is equal to 0. You know, which one's easier to do, right? They're the same thing. But solving derivative equal to 0, that's also learning math. That's the interpretation of this right here. All right, so this is key to your interpretation of what you need to do. So y equals negative 3x squared minus x. We're going to take the derivative. We'll leave the negative 3 alone. The derivative of x squared. Look, I've already been sloppy here. I bring the 2 to the front. I leave the x. The exponent is 2 minus 1, which is a 1, so I didn't write it. Minus sign, x. If I have the equation y equals x, what's my slope? My slope is 1. It's always the coefficient. Negative is here, so I have a negative 1. The derivative of negative x is negative 1. Simplify. Negative 3 times 2 is a negative 6. So negative 3 times 2x is a negative 6x minus 1. I want the tangent line is horizontal, so I'm going to set my slope, my derivative, equal to 0. Add 1 to both sides, divide by negative 6, and I find that when x is a negative 1/6, the tangent line to the graph is horizontal. And I think what you might find is if you graph this, what you're going to find right here is a vertex. Right? Tangent. Look at that. I encourage you to pause, open up a new window, hit desmos.com/calculator, graph this, and notice that your vertex is here at x equals negative 1/6. That's a preview. We're going to get some good stuff out of this. Same thing, where the tangent line to the graph is horizontal, find the x value, so the derivative is 0. We start with the function y equals x minus square root of x, and my first step is always write it with rational exponents, because radicals don't have rules. They're radical. My derivative, the derivative of x, is 1. Anytime the x has a power of 1, the derivative is just the coefficient, so 1. The derivative of minus x to the 1/2, that's a minus. Bring down that 1/2. Leave the x, subtract 1 from the exponent. So we'll have 1 minus 1/2 x to the negative 1/2. That x to the negative 1/2 comes down to our denominator to become a positive exponent. And finally, I take it back. We started with a radical. I used rational exponents, but I'm going to take it back to a radical so that I can solve. So I found my derivative, and then I simplified back to my original format. Once I'm here, now I can set the derivative equal to 0. 0 equals 1 minus 1 over 2 square root of x. I added 1 over 2 square root of x to both sides. All right, left the 1 on this side. Denominators, let's multiply both sides by the denominator, 2 square root of x. 2 square root of x times 1 over 2 square root of x. The 2 square root of x's cancel out, and I'm left with a 1. 1 times 2 square root of x is a 2 square root of x on the right. So really all I did is get the 2 square root of x out of the denominator. Divide by 2. Once I isolate that square root of x, I have 1/2 equals the square root of x. I'm going to square both sides. 1/2 times 1/2 is 1/4. The square root of x times the square root of x is x. And I found x equals 1/4 as where the tangent line to the graph is horizontal. Check out the graph. Look at it. Look at that spot. See what this function does. What's going on at x equals 1/4? All right, there's some important things going on there. All right, last one, the last thing, and I'm going to tell you right now, this is one of the coolest results for me in all of calculus, and you're learning it in your first semester of business calculus. Our math people, math and engineers and all that, we don't teach this until the second semester. All right, super valuable, super important, super useful, but you're seeing it a lot earlier in your math development than mathematicians. So here you go. Here's the key to awesomeness. This is called L'Hopital's rule. He is French. The H and the S are silent. L'Hopital's rule. If f and g are two differentiable functions, so derivatives exist, such that substituting x equals a in the expression f of x over g of x gives either 0, 0 or infinity over infinity. These are called indeterminate forms. Indeterminate forms because 0 over 0, as it turns out, I can make that be any number you want it to be. I can make that happen. So we have to do some more work when we get indeterminate forms. Okay, so if the original function, when we evaluate, gives an indeterminate form, then the limit as x approaches a of our quotient of two functions is the same as the limit as x approaches a of their derivatives. So the ratio of two functions is very similar to the ratio of their derivatives, is exactly what this is saying. So we can replace f of x and g of x with their derivatives and try again to take the limit. This is pretty cool. The limit as x approaches -1 of x squared plus 3x plus 2 over x squared plus x. Now, when I first substitute -1 in for x, right, because that's always what we want to do with limits. That's -1 squared plus 3 times -1 plus 2. That's 1 minus 3 plus 2. Denominator, -1 squared plus a -1. That's a 1 minus 1. I end up with 0 over 0. If I want to evaluate this limit, I get an indeterminate form. But L'Hopital said, hey, check out the derivatives. The derivative of x squared is 2x. The derivative of 3x is 3, right? A line, y equals 3x, has slope 3. And a constant has a 0 derivative, so I didn't even write the plus 0 here. In the denominator, x squared has derivative 2x. What's the slope of y equals x? That slope is 1. All a derivative is a slope. So evaluating f of x over g of x, this rational function, looking at it as two separate pieces, a numerator separate from its denominator and not a single fraction. We could take the derivative of the numerator and the derivative of the denominator, and we can evaluate the limit again. And this time when we put it in, when we evaluate, we'll end up with 1 over -1, which is -1. So in this case, for this function, this limit, 0 over 0 could be equal to -1. If we try this again, the limit as x approaches 2, when I evaluate the function, I end up with 0 over 0. Because it's 0 over 0, this is an indeterminate form, I can use L'Hopital's rule. When I use L'Hopital's rule, I'm going to take the derivative of the numerator. Derivative of x squared is 2x. The derivative of minus 3x is a minus 3. And the derivative of plus 2 is 0, so I didn't bother writing it. The derivative of x squared is 2x minus the derivative of x is 1 minus the derivative of 2 is 0, so I didn't write a minus 0 or a plus 0 because they're zeros. Boring. I'm not going to add them. But I can now take my limit. As x approaches 2, I evaluated the 2. I'll end up with 1/2. Indeterminate. We cannot determine what this value is forever and always. Sometimes 0 over 0 is -1. Sometimes 0 over 0 is 1/2. Right? It just depends. So let's look at another limit. The limit as x approaches 1 of x squared minus 4x plus 5 over x cubed minus 1. When I substitute and put 1 in, I'll get 1 squared minus 4 times 1 plus 5 over 1 cubed minus 1. Well, 1 squared is 1. 4 times 1 is 4. So 1 minus 4 is a -3. -3 plus 5 is 2. 1 minus 1 in the denominator is 0. We cannot use L'Hopital's rule. You could take the derivatives, you could take the limits afterwards, but that's not guaranteed to give you the correct answer. Because this is not an indeterminate form, I cannot use the rule. To evaluate this one, I'd probably use a table. I don't know, I'd use a graph, but at the time I was writing these notes, I didn't have something awesome like Desmos to pop in. So I'm going to let x go to 1 from the left. I'm going to let x get closer to 1 from the right. I see that this graph turns out as we get closer and closer to 1, it's coming down here and it's going up there. The limit does not exist. All right, so watch for that. 30-minute lecture. I'm so sorry. I'll try to make the next one shorter, but I don't want to go too quick. 11.2 coming soon.